Okay, an excuse for choosing this topic of nonlinear electrodynamics is the fact that these models celebrate their 90th anniversary in this period, and the topic starts from the famous Born-Infield electrodynamics proposed in 33-34, and it remains basically the most famous theory because as we all know, it has a lot of important applications in string theory. Another electrodynamics of nonlinear electrodynamics is the Euler-Heisenberg effective theory proposed in 35, which is the most phenomenologically related to fundamental interactions which we observe, theory which describes the quantum electrodynamics in an effective way when matter fields like fermions or some charged scalars, if they are present, get integrated. But during these 90 years, people proposed a huge number of models which come with some strange names like logarithmic, double logarithmic, exponential, rational, and others. And they were proposed in different contexts and for different purposes. And basically, nonlinear electrodynamics is an area which is applied in several directions of research. For example, these kind of models have been used to consider some black hole solutions, in particular looking for regular black hole solutions in Einstein theory and beyond. Then these models of nonlinear electrodynamics were also used to, for example, resolve the Big Bang singularity or describe inflation and dark energy. And also in the area of condensed matter theory and optics, it has many applications, including the description via the ADS condensed matter theory correspondence. And the latest example of these theories was found quite recently by Igor Bandas, Kurt Lechner, Paul Townsend, and myself. And it's a curious example because we were working on a completely different problem. Well, maybe not completely different. We were studying a tensionless limit of M5 brane of M theory. But then Kurt Lechner came with some very simple but question: what is the theory which, like Maxwell theory, would be conformal invariant and duality invariant simultaneously, but would be non-linear? It's quite surprising that this question was not asked during all these years of the development of the theories. And it turns out that there is a unique theory of this kind which modifies Maxwell theory and still remains electromagnetic invariant under electromagnetic duality and is conformal, classically at least. So in this talk, I would like to review some basic features of net theories and concentrating on Mond-Max theories. We'll discuss some of its solution and implications, and especially in the context of new TTbar-like deformations of field theories with stress energy tensors. So let me start with the definition. What is the nonlinear electrodynamics? It's a theory which generalized Maxwell theory to a theory of self-interactions of electromagnetic fields. So the generic Lagrangian depends on the two possible invariants in 4 dimensions, which one can construct from the field strength of the electromagnetic field. This is a scalar and a pseudo-scalar where phi tilde is the Hodge dual of F. And usually we require that in the weak field limit, these theories reduce basically to Maxwell theory plus some higher order corrections. But as we will see, it's not always it does not happen always. For example, in the mod-max case, because it's conformal theory, there is no weak field limit, but the theory reduces to Maxwell theory in the zero limit of its parameter. Let me give an example of the Heisenberg-Euler theory, which, as I said, the most close to phenomenological applications. So in the Heisenberg-Euler theory, these coefficients are very small. As you can see, the B is related to A in this way, and A is constructed from the fundamental constants of electrodynamics, so the Planck constant, the fine structure constant, the mass of electron, the speed of light, and so on. And the value of A is 4 × 10⁻25 of Tesla in the units of magnetic field. So the effects, quantum effects of quantum electrodynamics are really small. And only recently in CERN, several years ago, this CERN has managed to measure, for example, the photon-photon scattering, which is in agreement with the value of these constants. Now, what we would like to have in this nonlinear electrodynamic theory, what kind of properties we would like that these theories have. And the first is, of course, the consistency of the theory, for example, causality and unitarity, which restricts the form of this Lagrangian. There has been activity on finding the conditions of the Lagrangian, for the theory to be, for example, causal, and in very recent work by Jorge Russo and Paul Townsend, they have found the most general conditions which the theory should satisfy for strong causality. And the basic condition which enters in the definition of these properties is the Hessian, which one constructs as a second derivative of the Lagrangian with respect to the electric field, and the theory is causal basically when this Hessian matrix has all its eigenvalues non-negative. Then one may ask when the theory may be conformal, and this happens if the Lagrangian is a homogeneous function of degree 1 with respect to the rescaling of the electromagnetic field. For example, if we rescale these scalars S with some parameter A, then the Lagrangian should have this form, because then the rescaling with respect of the Lagrangian can be compensated with the rescaling of the coordinates here. And then another important property which we would like to have, for example, which we know that plays an important role, is the electric magnetic duality, which in the case of nonlinear theory has the X as follows. So we have the equations of motion here, which we get from the theory, which in the Maxwell case just reduced to F mu nu here. And then there are Bianchi identities. And then we would like to have the symmetry under which the left-hand sides of these equations are rotated by some SO2 matrix, and then we get some new fields phi prime and corresponding Lagrangian, which should have the same form as the initial one, and then we are saying that the theory is invariant under electric and magnetic duality, which imposes this condition on the Lagrangian of the theory first found by Belenitsky-Birula in '83. The famous example is the Born-Infeld theory, whose Lagrangian is, of course, well known, and T is the coupling parameter of dimension of energy density here, and it's associated with the D3 brane tension in string theory. So the important property of the theory is that it is duality symmetric. So its Lagrangian satisfies the duality invariance condition, which I have shown in the previous slides. And this was already noticed by Schrödinger in 35, but then exemplified by Bielanitsky-Birula in 83. And of course, we know that when T goes to infinity, this Lagrangian reduces to Maxwell theory. So what happens if we now require that the theory is, the Lagrangian also satisfies the conformal invariance condition in addition to duality invariance? And then it turns out that there is a unique theory, basically, which is this modified or Maxwell or mod-max theory, and its Lagrangian has the following structure here. So it has the dimensionless parameter gamma, which enters the Lagrangian under the hyperbolic cosine and sine. And the parameter should be greater or equal to 0. When parameter is equal to 0, it's a Maxwell theory. And this, the fact that it is greater to 0 is the causality condition which I discussed earlier. Then, so you see that this theory is basically non-analytic here. It has this square root. And the energy momentum tensor has this form. It is proportional to Maxwell theory times some scalar factor. And the energy is always non-negative, and the trace is equal to 0, which signals that the theory is conformal. So let me show the equations of motion which we have. So there is the linear piece and the nonlinear piece here, and from which we see that there is an ambiguity when S and P both goes to 0, so there is a 0 by 0 ambiguity of this kind. But the vacuum is still a well-defined solution, though, for example, the null fields and the plane waves, which satisfy the conditions that S and P are equal to 0, are not well-defined solutions in the Lagrangian formulation. But it turns out that if you go to the Hamiltonian formulation of the theory, then the plane wave solutions are full-fledged solutions of the theory. Of course, because of the nonlinearity, it's not easy to find solutions of the theory, but at least some simple class of solutions can be easily found. For example, when P and AS are proportional to each other, then these equations simplify and basically become linear. One solution which people intensively studied in these 4 years almost is the effects of this theory on the solutions of Einstein equations, and in particular on black holes. And the simplest example is the Reiser-Nordström solution modified by the mod-max fields. So we have the standard black hole metric ansatz here, and then it turns out that to satisfy the mod-max equations of motion, the Coulomb part, where Q is the electric charge of the black hole and Qm is its magnetic charge. So this is basically the Coulomb potential here, and it is modified by the gamma parameter in this way. And the function Fr has this form, so we see that the extremality condition for this Reiser-Nordström black hole is modified by the e to the minus gamma, the relation between mass of the black hole and the square and their charges. So for increasing gamma, we have a kind of screening effect. One can have less massive black hole here. And people studied more general solutions of this kind, like tau-NAT accelerating black holes, Robertson-Trautmann spaces, black hole thermodynamics, and found how the dependence on gamma affects the behavior of this object. One of the open problems which I would like to raise here in this part of the talk is that the rotating black hole solutions have not been found yet. Not only in the MODMAX theory, but in general, there is a kind of abstraction or a problem of finding rotating black hole solutions for a general class of nonlinear electrodynamics, and that might be an interesting, challenging problem to study. Okay, now I think it's time to pass to the second part of my talk, which is related to the TTbar-like deformations in Maxwell's electrodynamics and more general in different theories in various dimensions. So it was triggered by the structure of the MODMAX Lagrangian. And so let me say just a few words about what are TTbar deformations, how they started. So they were put forward by Zamolodchikov in 2004 for deforming two-dimensional quantum field theories and CFTs with the use of some composite irrelevant operator built of the components of the stress energy tensor in such a way that the good properties of the initial theories remain after the deformation of the theory with these irrelevant operators, in particular integrability and other quantum properties of the theory. So the deformation, as it was proposed, it works as follows. We start from some Lagrangian of initial or seed theory and some operator composed of components of the energy momentum tensor, then recompute the energy momentum tensor for this additional deformation, substitute it into the second order, and so on. And then in the end, the assumption is that this series of deformations closes to some expression, and one gets the so-called flow, TTbar flow equation, which says that the derivative of the final theory we get upon deformation with respect to the deformation parameter is equal to the operator we used at each step to deform the theory. And the most prominent operator which people used in 2 dimensions is 1/4 of the determinant of the of the energy momentum tensor, which is the well-defined operator, local operator in the quantum theory. So that was the main requirement for choosing this form of the deformation. Then, much later, people started to study whether in higher dimensions there are deformations of this kind, and they found that, for example, the Born-Einfeld theory in 4 dimensions can be also treated as a energy momentum deformation of Maxwell theory. So it was found that if you take the Born-Einfeld Lagrangian and take its variation with respect to inverse of the tension parameter, then this derivative is equal to the following combination of the energy momentum tensor of Born-Einfeld theory itself. And it turned out that this MODMAX theory also can be treated as a TTbar-like deformation, but with a different operator, which is irrelevant here, because the operator, so we take the derivative of the Lagrangian with respect to the gamma parameter, and we find that it is equal to this square root of this combination of the components of the energy momentum tensor here. And so this observation triggered the development of so-called root TTbar deformations of theories in different dimensions, and in particular in 2 dimensions. And so let me just show this diagram here, which shows how the Maxwell Lagrangian in 4 dimensions can be deformed, but also the same diagram can be applied in other dimensions, for example, in 2 dimensions or 6 dimensions for getting deformed theories. So if you start with the Maxwell Lagrangian and require that the deformed theory with respect to some parameter satisfies this condition, we find that the resulting theory is the Born-Infield theory. Then we can deform this theory with a this marginal operator and get something which is called mod-max Born-Infield, which I'll show in the next slide. Or we can go in a different way. We can deform first the Maxwell to mod-max using this operator, and then apply the same operator we used for the Born-Infield theory to get the same theory. So the 2 deformations of, in this case, commute and give this new theory, whose Lagrangian has the following form. So in comparison with the standard Born-Infield, where there was this f mu nu squared under the square root, here, instead of f mu nu, we basically have the Lagrangian of mod-max theory. So this is the generalized mod-max Born-Infield theory, which one gets upon the specific TTbar deformation of Maxwell theory with 2 parameters. How much time do I have? Not very much. Okay, let me 5 minutes. Okay, I think I will just skip mentioned briefly. So what has been done in this TTbar business upon noticing that there is a new root TTbar deformation with the marginal operator. So the mod-max theory and its Born-Infield generalization was reduced to 2 dimensions, and people found new theories of scalar fields which can be interpreted as TTbar deformations. An interesting observation recently, which goes beyond mod-max theory, but it concerns all class of nonlinear electrodynamics, is that the TTbar deformations of these theories can be reinterpreted as some coupling of the usual initial theory to gravity. The general discussion of root TTbar deformations has been considered, and then an interesting result was by Barsato, Ferco, and Sfondrini that classical integrable models like principal chiral models or symmetric space sigma models remain integrable even upon the root TTbar deformation. For example, the deformed PCM model has this form with J being the currents of a certain gauge group here. Another interesting observation was that there is a an analog of two-dimensional mod-max-like oscillator, which is exactly solvable theory and fully quantizable theory in, say, one-dimensional mechanical system. There was work on the relation of TT-bar deformations in the context of ADS-3CFT2 correspondence and in the context of coupling these models to Jacob Teitelbaum gravity and others. Recently, we have also considered these TT-bar-like deformations, including Mod-Max-like chiral two-form theory in 6 dimensions, and there are many other directions which I have not had time to mention. So let me conclude just with some open problems. One of the problems is some fundamental origin of say, Mod-Max theory. We know that nonlinear electrodynamics models should be considered as effective field theories, and only for few of them, like Born-Infeld theory, we know their origin. For example, Born-Infeld is related to string theory, and as I mentioned, Heisenberg-Eller's theory is related to QED. So one may ask what is the fundamental origin of Mod-Max, and some hint is that this theory might be some theory of Maxwell theory coupled to axionic-like scalar field. So another question which I may ask, is there any interpretation of Mod-Max and is Born-Infeld generalization in string theory? And this question was addressed by Nastase, for example. Then one may ask whether there are 6-dimensional supersymmetric versions of chiral two-form Mod-Max theory and Born-Infeld. And the 4-dimensional supersymmetric Mod-Max theories do exist, which they have been constructed some time ago. And another topic of interest is to have a more deep insight into the implications of the TT-bar deformations in different dimensions, and in particular root TT-bar from the point of view of quantum theory. The standard TT-bar deformations are well defined at the quantum level, but the root TT-bar deformation is only understood at the classical level, and even in 2 dimensions. Though, as I have mentioned, in 1 dimension there is an example of completely quantizable theory of this anharmonic oscillator. Then one may ask the question if the effective action of Mod-Max theory have any sensible structure, and there are some preliminary results in the literature about this topic. And then I think the interesting topic is the study of TT-bar-like flows or energy momentum deformations of the chiral 4-form gauge theory in 10 dimensions, which may be related to the construction of S-duality invariant high-order corrections to the action of type 2b supergravity. So I will stop here. Thank you very much.
Thank you, Dima. Questions for Dima? Yes.
Just one comment. At the beginning of the talk, you said that you can use nonlinear electrodynamics to support regular black hole solutions.
Yes.
That's ruled out now because any causal theory obeys the strong energy condition. And if the strong energy condition is obeyed, then the singularity theorems by Penrose implies that there must be a singularity. So no causal nonlinear electrodynamics can support a regular black hole solution.
Even for purely magnetic case, or you are talking about electric black holes?
In general.
In general, either electric
causality implies the strong energy condition, and that implies singularity.
That implies that any even magnetic
Even
cases
magnetic,
rule
yes.
that. Okay, thank you.
Yes?
So thank you. No, just a comment to Jorge regarding this discussion. So actually, the theory of nonlinear electrodynamics discovered by John Beato and Garcia, I insist that they have a small issue that people overlook, is that the Lagrangian depends on the parameters of the solution. So to say, the Lagrangian depends on the electric charge that you have to introduce in the solution in order to have a regular solution. So therefore, this is the way in which they manage to cook a theory in which they find this regular solution, because actually one can argue that that the parameters of the theory are fine-tuned with the corresponding solution. So this is the way in which they manage to do that. So and then if you want to find regular black holes in the context of nonlinear electrodynamics, as Jorge was saying, in order to break the singularity the singularity theorems of Penrose, then you could go to higher quadratic corrections, and then by including higher quadratic corrections, you can indeed obtain regular black holes. But this was just to clarify Jorge's comment.
Thank you. Any more questions or comments? Yes, one. I'll give you the mic.
Some small question. What about, you told about 2D modmax oscillator, mechanical system, and told that it is exactly solvable.
Yes.
But is it superintegrable or not? It means that, is it superintegrable system or not? Did you present its constants of motion additional?
Yes, in this sense, I think yes.
In this sense.
It is.
But spectrum is non-degenerated.
No, as far as I remember.
Okay, thanks.
Okay. I think in view of time, it's time to thank Dima again.